Okay, so last week we went through a bit on the electric field chapter. I told you that Fe is actually your electric force is 1/4 pi epsilon naught QQ over R squared. And then electric field strength is 1/4 pi epsilon naught Q over R squared. All right, and then after that, I also mentioned to you that this is only applicable for 2-point charges. Only 2 charges, and the charges must be point charges. Okay. Now, there will be cases when you look at your questions later on that they tell you that they have 2 separate charges, and then after that they're interested in the region in between the 2 charges. Okay, typically you have a charge A and charge B, and then they're interested in the region between the charges. So before we go to that, last week I actually did mention to you, if say for example right now I talk to you about charge A itself and charge B itself, if I consider those charges individually, I could say that charge A would have its own electric field strength. So sorry, would have its own electric field that looks like this. Charge B would also have its own electric field that looks like this. Okay, so this one, since it's positively charged, and then this one is also positively charged, you expect that the direction of your electric field strength to be like this, going outwards, right? Then after that, this is assuming that they are each very far apart from each other so that they don't affect each other. But what if you bring them closer to each other? This comes to here and then this comes to here, such that they're close to each other. What will then happen is that you will have your charge A here, you will have your charge B here. The electric field of charge A and electric field of charge B will actually now combine to give you a new resultant electric field. Typically, it will look like this. In your SPM or IGCSE, you would have been exposed to how 2 charges, the electric field would look like. In your case, it will look something like this. In your IGCSE or SPM questions, you will have been tested on what is the possible electric field between 2 positive charges. I do not know whether you remember about that. So, but the thing is that you should know that we did mention that before, sometime in your previous education level. So in your case here, when these 2 charges are now brought close to each other, the idea is that the electric field of both charges will now combine to give you a new electric field. So you're interested in this region here. So whatever is this about the electric field here, you know that it is actually due to the combination of this charge and this charge. Okay, so when you're talking about the region in between these 2 charges, you know it is due to the combined effects of each of the spheres individually. So whatever you have here, you just need to add them up. You need to add the combined effects of each sphere individually. So typically we will ask you to find out what is the electric force on the charge here, what's the electric field strength here, what's the electric potential, what's the electric potential energy here. Okay, so like in your case, if say for example right now I am interested in finding out what is the electric force on a positive test charge placed in this field, I consider the effects individually first before I combine them. If I put a positive test charge here, my electric force due to A would be in this direction because positive will repel positive, whereas the electric force due to sphere B on the positive test charge will be in this direction because again positive repel positive. So when I want to add them up together to find out what's the resultant force, it will be Fp equals to Fa plus negative Fb. Why is there a negative here? Because force is a vector. You need to take into account their direction. If you see that one of it is acting in the opposite direction, so you will have a negative. Okay. Then after that, if you wanted to expand your equation further, you know that Fa plus negative FB here. So this FA here, you notice is actually between the positive test charge and your charge A. This is now considered 2-point charges, right? You have 2 charges only, and they can be considered as point charges. So I can make use of this equation. So it will be 1 over 4 pi epsilon naught QA multiplied by Q over RA squared. Your RA is the distance between charge A and the test charge. Okay, then after that, when I look at the force due to B, it will be this one here. So again, there are 2 charges, and I can consider them as point charges. So again, I can use this equation. So it will be 1 over 4 pi epsilon naught QB times Q over RB squared. But in your case, RB is here, the distance between charge B and the positive test charge itself. Okay, then you get this expression here. Now then, if you were to try and find out another separate quantity called the field strength here, your analysis would be the same. I need to find out what is the field strength due to A and field strength due to B individually first before I add them up. So in my case, if I put a positive test charge here, I already know that the force on the positive test charge due to A is going to be in this direction. So my electric field strength will also be in this same direction. And then likewise, if I'm talking about the effects due to charge B, the force on the positive test charge here due to B is already in this direction. So EB is in this direction. So when I want to add them out together, it will just be EA plus with negative EB. Then after that, when I look at it separate, when I look at it, EA is between this, EB is between this. So I can again use this equation again. So I get 1 over 4 pi epsilon naught QA over RA squared minus 1 over 4 pi epsilon naught QB over RB squared, right? Then after that, you get the expression. So you will often be asked to draw a graph to represent the variation of the field strength as well as the electric force between the 2 charges. So typically, all you just need to know is that it will just look like this. Now, the easy way to think of it is, why does the graph shape look like that? Look like this is by thinking it this way. You see, if you're talking about FA and FB, EA and EB, they are always in the opposite direction. So it will come to a point where FE is equals to, say for example, I just talk about field strength. I don't want to talk about force because the analysis is the same. If I talk about field strength alone, I would know that there will be one particular point where EA is equal and opposite to EB. Meaning to say EA equals EB. So my resulting electric field strength is 0. Okay. But then if I go, if say this one is the point where EA is equals to EB, where my field strength is equal to 0, what if I go a bit more towards the right of this point or a bit more towards the left of this point? If I go a bit towards the right a little, I go towards the right of the point where E is 0, you will have a case where you have a net field strength. If I go more towards this side, what you could see is this. If I go more towards this side, my RA is considered to have increased. My RB is considered to have dropped. Okay, because this is RA and RB, right? RA would have increased, RB would have dropped. What then this would mean is that my EA, which is given by this, would actually now drop, but my EB will actually now increase. So based on this one, you see that if I go towards the right, EA would now drop, EB would now increase. So you come to a conclusion that your EB here will actually be more than EA. So if EB is more than EA, that will mean that your E is going to be towards the left. Okay, because EB itself is already towards the left. If your EB is more than EA, that means your net electric field strength is going to be towards the left itself. All right. Then if I try the same analysis for a case where it is on the right side, sorry, left side here, or the point where E is 0, I will be able to see that it is actually the opposite. If I go more towards this side, my RA is considered to have dropped, my RB is considered to have increased. So in turn, this means that EA would increase, whereas EB would drop. So in that case here, if EA is increasing but EB is dropping, if I go more towards this side, EA would now be more than EB. So my direction of my resulting field strength would now actually be towards this side. Okay, that's how you will see it. You will be able to see that there will be one point where the resulting field strength is 0, but at one point the resulting field strength will now be at the opposite direction. In your case, you go towards the right, you'll be towards the left. If you go towards the left, now the resulting electric field strength will be towards the right. Okay, so in that case here, you will see that as you go along your distance from one end to another end, you will notice that your field strength will be positive, then you change to a negative. Because you see, field strength is actually a vector. If you have a negative, that simply means that you have changed direction. Okay, negative to vectors means that it's already acting in the opposite direction. So here, you could see that if I go from here, if I have a positive test charge that move from here all the way to here, here to here, the field strength will be acting towards the right. At this point here, field strength will be 0. Then if I continue moving from here to here, field strength would now be acting towards the left. For this case here, my field strength is still considered to be positive. But for this case here, my field strength is considered to be negative because I have changed direction. So the graph shape that shows that is this one. Okay, that's the easy way to interpret this. The actual way to get this graph shape is by you subbing in all the values of x inside or r and rb here. Eventually you get this, but the easy way to look at it now is by looking at this. Okay, because there are cases where they will ask you from the given graph, explain whether the charges have same sign or opposite sign. So the easy thing would be to look at this one. This one, E is vector, so direction is important. Okay, so direction has to be taken into account. Okay, in my case, I'll just say this. Direction has to be taken into account. So any negative means that E is in opposite direction. Okay, E is vector, direction has to be taken into account. Any negative means that E is in the opposite direction. Now there are cases where a lot of times we will just give you a graph like this and then ask you to identify whether the charges have the same sign or opposite sign. Sign here in the sense whether are they positive, positive, negative, negative, or positive, negative. So the easy way to look at it would be to look at it this way. You look at these values here. This one here, you see E is in opposite direction. Therefore, charges have same sign. The way to interpret that would be by looking at it like this. If I have a positive test charge, here I know that it will be 0. If I go more towards this side, because I'm closer towards sphere A, the effect of sphere A will be larger than the effect of sphere B. So whatever effect I have here is determined mainly by sphere A. If this is a positive test charge and this is positive, I know that my E will be in this direction. Likewise, if I go and put my positive test charge here, at this part here, I know that the effects due to B would definitely be larger than the effects due to A. The overall effect here is determined by B. So if this one is a positive test charge, I notice that my resulting electric field strength will also be in this direction. Positive, positive will repel, right? So electric force is in this direction, field strength is in this direction. So now when you look at a positive test charge placed here and here, the direction is opposite. So here you'll be able to deduce that, yeah, they definitely must be having same sign. The same thing can also be said if I tell you that this is negative, negative, you will still get the same conclusion that the field strength is going to be in opposite sign. Say for example, I give you a negative sphere A and I give you a negative sphere B. If I put a positive test charge here, whatever field strength I have here will be determined mainly by A. So this is negative, this is positive, my E will be in this direction. Then if I move my positive test charge towards here, again, whatever resulting field strength I have here will be determined mainly by B. Okay, so this is positive, this is negative, the electric force is towards the right, that means my E will also be towards the right. So when you look at this one, the direction of your electric field strength specifically, this one is going here towards the left, this one is going here towards the right. So when you try to draw the graph again, you notice that there will definitely be a point where they have, I mean, at both ends representing the location of both spheres, you will definitely have field strength in opposite direction. Meaning to say you will see that field strength would have opposite signs here. Okay, the moment you see there is an opposite sign here, it indicates to you that the field strength is in opposite direction. That means the charges are having same sign. That's how you interpret it. Okay, it may not make much sense to you, but later on the questions you see from there. Okay, so just bear this in mind first. This is the way we normally do. We look at the sign of the E, whether it's positive or negative. If it's positive or negative, that means they're in opposite direction. That means the charges would have same sign here. Okay, right. So this one is explaining the graph part. Then after that, there will also be a case where sometimes we will ask you to deduce from the graph whether a positive test charge will actually be speeding up, slowing down when it is moving from one end to another end. So let me just explain that to you. So let me rub this one off. Okay, so now if I consider a case where I have a positive test charge, like this one, that's moving from here to here, then here to here, and then here to here, I'm interested in knowing whether is it speeding up, slowing down, or moving with constant velocity. So the easy thing to look at would be to look at this one here, the graph here. This graph here represents the variation of the field strength as well as the electric force when going from position of sphere A to position of sphere B. Now, if for example right now I look at the electric force, the electric force analysis will be same for this one. You understand that whatever electric force you have between here and here is determined by electric force due to A and B combined together, but one of it will always be opposite direction to the other. So there will be a point where the electric force is going to be zero. There will be a point where the electric force is going to be more than the other. If like for this case, I move towards this side, you could understand that the electric force ought to be towards the left because FB will be larger than FA. And then for this case here, if I move towards the left side, FA will be larger than FB. So my electric force will be towards the right. Okay. To make it simple, I think I better just write it down. Here, you will have F net equals to 0. Here, you will have F net going this direction. Here, you will have F net going here. All right. That is basically your resultant electric force now. Okay. So if you have a test charge that is now moving from here to here, you notice that your net force is actually going to, when you're moving from here to here, your net force is acting in the same direction. The direction never changes, but its magnitude will decrease. You will see it from here. if I move from here to here, my net force is still in the same direction because the sign did not change. It's still positive throughout. That means the direction of the net force did not change. But you notice that the magnitude is progressively decreasing. That means that my net force here is decreasing if I'm moving towards the right, but my net force is decreasing. What you will say is that you are actually speeding up, but at decreasing rate. Okay, maybe I need to draw this somewhere. If I'm going this side, my velocity is this side, but my net force is again in the same direction. I know I will speed up, but the net force is decreasing in magnitude. So my acceleration is decreasing in magnitude. I am speeding up, but at decreasing rate. Right, I'm still speeding up, but not as much as before. Okay, so that is what we mean by that. Then after that, at this point here, where my net force is 0, or where my acceleration is 0, I could also say that if here to here I was speeding up, then after that here I start to have an acceleration equals to 0. That means my speed cannot change any further. When your net force is 0, that means your acceleration is 0. If before this you are speeding up, then suddenly your acceleration here is 0 because net force is 0. Your speed cannot change any further. So that would mean that here you have reached max speed already. Because previously you're speeding up, then up to this point, your acceleration suddenly becomes 0. Acceleration being 0 means velocity cannot change any further, speed cannot change any further. So here you reach max speed. Okay, but after you pass this point here, as you continue to move, your net force has now changed direction. It is now acting towards the left. So if you're trying to move towards the right, well, but your net force is towards the left, is in the opposite direction, you know that you're gonna slow down. But are you going to be slowing down uniformly at increasing rate or decreasing rate? You have to look at this one. If you go from here to here, your net force is going to be in opposite direction already because all of it is negative. That means it's in the opposite direction. So you are going to slow down, but then you look at the magnitude of your net force. It is getting progressively larger. That means your acceleration here in the opposite direction is getting progressively larger also. So in your case here, you are slowing down, but at increasing rate. Okay, that's in general how you look at it. Okay, that what I explained just now is actually described in sections 1, 2, and 3. Okay, sorry, sections 1, point between sections 1 and 2, and section 2 itself. So far, so good with that. So in order to let you have a try, I think I better just give you one question to look at. There is page 23. Yeah. Okay. Maybe it's better if I just illustrate to you with a question. Have a look at page 23 of your worksheet. This one will allow you to test what you've just learned. Have a look at page 23 of your worksheet. Okay. Right. Okay, so this one I'll just clear it off first. Okay, this one is March 17 P42. This is question 6A. Right. Now, is there a similarity and a difference between electric field lines and gravitational field lines around an isolated positively charged metal sphere? Okay. Now, this one is a positively charged metal sphere. Okay, so this one has positive charge. And then this one is metal sphere. That means this one has mass. It's a metal sphere, it has mass. So if I were to separate them, if I were to consider them separately, a positive charge sphere would have a field that looks like this. Okay, it will be radial and it will be pointed outwards. If I consider the mass part of the charge sphere, where I just consider the mass, the field, the gravitational field around the mass will be like this. Okay, but the direction will be inwards. Okay, positively charged metal sphere, I consider the two components, a charge and the mass component. The charge component will give you an electric field. The mass component will give you a gravitational field. Okay, because it's a sphere, your cross-sectional area is a circle. So when you try to draw your field lines will always be perpendicular to the surface. So it will give you the appearance of a radial pattern. Okay, so your similarity here will be that your field lines are radial. Okay, you could also say that there's greater separations of lines with increased distance from the center, but that is the effect of your field lines being radial. Your field lines is radial. The further you go from the center, you notice that the separation of your lines becomes even larger. But it's enough to just say that the field lines are radial. But what is the difference between your gravitational field line and electric field lines? It's just simply this. You remember that for electric field, your direction of electric field is determined by direction of force on the positive test charge placed in the field. So if this is positive and this is a positive test charge, your electric force is in this direction, your field direction will follow the direction of force on a positive test charge. If you're talking about a mass, the direction of force on a gravitational field, the direction of force on the test mass placed in the field would determine the direction of the gravitational force. You put a test mass here, this mass will be attracted to this, your Fg is in this direction, so your gravitational field would be inwards. Okay, so the differences here you will see is in terms of the direction. Gravitational field lines will always be directed towards the center of the sphere, whereas electric field lines will be directed away from the sphere. They differ only in the direction. Okay. Now this is what we call as isolated charge, isolated mass. Okay, this is isolated charge. This is isolated mass. There's no other charge nearby it. There's no other mass nearby it. We don't consider the test charge. We don't consider the test mass. Okay. Right, so if this one is okay, then you can look at part B. They tell you now you have a positive point charge, positive Q that is positioned at point X, and an identical positive point charge is positioned at fixed point Y, as shown in figure 6.1. The charges are separated in a vacuum by a distance of 10 centimeter. Points A and B are on the line XY here. The electric field strength at point A is 4.1 times 10 power minus 5 volt per meter. Calculate the charge Q here, right? So based on the situation that you have here, this one here is not considered to be an isolated charge. Okay, let me just clear this one off. Now when you look at this one here, this is a case where you are talking about a case between two charges. They tell you you have a charge at point X, you have a charge at point Q with a magnitude of positive Q, with a magnitude of positive Q also. So you're talking about the region. Whatever they're asking you right now is that they're telling you about the properties in the region between the two charges. In your case here, this one you cannot consider as isolated charge. Okay, you're talking about case of between charges where there's a resultant field in between. So now they tell you that the electric field strength at point A is actually 4.1 times 10 power minus 5 volt per meter. And then they ask you to calculate the magnitude of charge Q. So this one here is where you're talking about a case of between two charges. So you will have to realize that whatever property you have here is due to the combined effect of this and this together. So now they tell you the electric field strength at A, you're supposed to recognize that whatever electric field strength at A you have is due to the electric field strength of X and electric field strength of Y combined together. So in this case here, you have to first consider their effects separately before adding them up. So if I were to put a positive test charge here, sphere X or charge at X, because it's also positive, it will cause a electric field in this direction. This is effects due to X. If I consider effects due to Y on a positive test charge, this is positive, this is positive, so my EY will be in this direction. So my EA is this plus this, but because they are vectors, one of it, because they are vectors, direction has to be taken into account. So if this one is in opposite direction, this one will be negative. So it will be EX plus with negative EY. So you get this. Okay. Then, as mentioned just now to you, EX will be between this one and this one. This is 2-point charge. EY is between this and this. Again, it's 2-point charge. So I can straight away use the equation for E, which is 1 over 4 pi epsilon naught Q over R squared. So now I use the equation straight for X and Y. I get this. Right? This one is QA. This one is QB. I will still use the same Q because they already given me the magnitude here. And then after that, the thing here is that you're talking about your R, right? Your R is always the distance between the two charges. In your case, for X is between this charge and the positive test charge. This one is your Rx. For B, for field strength due to Y, your distance must be between the charge and the test charge. So this one is your Ry. That's why you get this. Okay, so you get Rx squared, Ry squared. The one, then after that, the Q, you factorize it out and you will be able to get your answer. So your Rx is 2.5 centimeter. Your Ry is 10 minus 2.5. You get 7.5 centimeter. So eventually when you do it, you make sure you change your answers to meter. Remember to square your answers. Eventually you get your answer Q as 3.21 times 10 power minus 18 coulomb. Okay, so you get the answer as that. Alright, so maybe I'll give you a minute to digest this. If you're okay with that, then you just look at the next page. Alright, so I'll clear this one out. Alright, so the values of the constants epsilon naught is 8.85 times 10 power minus 12. Alright. And you get your answer. And this one should be okay. Alright, so I assume this one you guys are okay already. Then I'll move on to the next one. Now, on figure 6.2, sketch a variation of the electric field strength E with distance D from A to B along line AB. they're asking you to sketch the variation of the field strength from A to B, which is from here to here. Okay, not really here to here, but from here to here. Okay, now here you already found out that your electric field strength is 4.1 times 10 power minus 5, correct? Now, what do you suppose will be your electric field strength here? Now, just now for the case where I told you if you have positive charge here, you should roughly know that the graph of field strength versus distance will look something like this. Okay, that time I mentioned to you, you should be able to realize that there'll be a point where your E is 0, there'll be a point where, or rather a range where your E is in one direction, and then another point where your E is in the opposite direction, right? Simply because at one side, one of the E will be larger than the other, and then on the other side, the other E will be larger than the other. So you should recognize that in my case here, when you put a positive test charge, depending on where you are, depending on where you move, the electric field strength direction will actually change. There'll be one point which is 0, there'll be one point where it's in one particular direction, and then on the other side, it'll be in another opposite direction. So then the graph shape will look like this, right? The thing I mentioned to you to look at is the fact that they have opposite sign. So meaning to say opposite direction of field. Okay, so now here you know that this one here is 4.1 times 10 power minus 5. Okay, and then after that you know that the more I go towards this side, eventually my field strength will change direction. Okay, there will be a point where it is actually 0. Now if you look at this one here, notice that this is same charge, and then the distances of A and B are also same, 2.5 centimeter, 2.5 centimeter. They are symmetrical. In all aspects, they are symmetrical, you see. Same magnitude of charge, same distance considered. So the thing here would be that where you expect your E will be 0, is actually going to be right in the middle. At 5 centimeter, you expect the E to be 0, right? But if measured from A, it is 2.5 centimeter. Okay. Now, B is 2.5 centimeter from Y. A is also 2.5 centimeter from X. If you were at 2.5 centimeter from X and it gave you the E equals to 4.1 times 10 power minus 5, because the symmetry is symmetrical here, you also expect that the field strength here will also be 4.1 times 10 power minus 5, but opposite direction. So it will be negative. Okay, so when you want to draw your graph, be careful of what they say. They want only from A to B, which is from here to here. So this one here is another 2.5 centimeter, right? At A is 4.1 times 10 power minus 5, it will become 0 right at the center at 2.5 centimeter from A. And then after that, as I keep on going further, eventually at B, I'll get back the same magnitude, but opposite direction of the field strength. So your graph will now look like this. Okay, the 0 here is you measuring from A. It will be 4.1 times 10 power minus 5. And then after that, as you keep moving, you suddenly will reach 0. That one will be right at the center. It's actually 2.5 centimeter from A. Then as you keep on moving, your field direction or your field strength will now change direction. It will become negative. So, but because there's symmetry, At point B, you get back exactly the same magnitude, just that it has a negative sign. And this is what you get. Okay, so that is for this one. Alright, so just indicate these points now. That's all I can just mention to you. Just indicate this point, this point, this point, and then after that, just start drawing the lines, and you're good to go already. Okay, right. Then after that, this is the part where you need to talk a bit about the motion of the object. So let me just clear this one off. All right. Now they tell you a small positive test charge is placed at A. The electric field strength causes the charge to move from rest along line AB. Describe the acceleration of the charge as it moves from A to B. Okay. Now, this is the, maybe I should just draw here. This is the variation of your electric field strength versus distance. You know, it looks something like this. This is your E versus X. Okay. And then we tell you that you have a positive test charge that you are moving from here all the way to here. Okay. Now, along the way, your E will be like this and like this. Okay. Let me just give you a few illustrations here. Okay. The 3 points of interest from you moving from here to here, here to here, and also at this point itself. Now, E is actually Fe over Q. So Fe is QE. And then Fe itself is the one that gives your charge the resultant force. In your case here, when you have a test charge moving from here to here, the only force acting on it is your electric force. The electric force is actually your net force here. It's actually your net force that gave you your acceleration. This is your F net. And because you know that F net is equals to ma, according to Newton's second law, you can actually re-expand this to become ma equals to qe. All right. Then after that, you could see something here. Your mass does not change. The mass of your charge did not change. The charge of the test charge itself did not change. You can say that m and q is constant. So therefore, A is proportional to E. Okay, A is actually directly proportional to E. So now I can actually now do something now. If I am moving from here to here like this, my E is in this direction. Sorry, my E is one particular direction. My A is also following the same direction. My A is here in this case right now. Okay. If I have a positive test charge that I move from here to here, I recognize that my E was in this direction. But at the same time, my A will also be in the same direction because E is proportional to A. So now I move from here to here. My A is in the same direction also, but the magnitude is decreasing. So I can say that the acceleration is decreasing. As I am moving from here to here, my acceleration is decreasing. It decreases to 0 at midpoint. Okay. Then after that, after the midpoint here, when I'm moving from here to here, my E has changed direction because there's a negative sign here, right? My E has now changed direction. It is now opposite. But at the same time, my A will also change direction along with it because E is proportional to A. All right. But then now I look at the magnitude. the magnitude is increasing. They're now in opposite direction, but the magnitude is increasing. So I could say that the acceleration will now increase in opposite direction. Hence your answer looks like this right now. Okay, acceleration of charge is proportional to electric field strength. As it moves from A to B, the acceleration will decrease to 0 at midpoint, which is talking about this point and this point. And then after that, acceleration will increase in opposite direction, which is from this point to this point. Okay, that's how you look at the graph. It takes some getting used to, but I think you guys should be okay. Okay, so if this one you are okay, then we move to page 27 before I continue back a little. Have a look at page 27. Okay, so this one is one example. Have a look at page 27 if you guys are okay with this. 27. Okay, so page 27 would be this one. Okay, actually the start of the question is on page 26. All right, go to page 26. A student 17P42. This is question 6. Okay, now state Coulomb's law. Coulomb's law is basically this one, the one that you use to explain electric force. Coulomb's law is just telling you that the force between 2-point charges is directly proportional to the product of the charges and inversely proportional to the square of the separation, which gave you this equation in the first place. So for this one, I would just skip it because it's just a definition question that you can just copy from the notes. So this one, I'll just skip it. I'm more interested in this one. Okay. Now, they tell you two charged metal spheres A and B are situated in a vacuum as illustrated in figure 6.1. This is sphere A, this is sphere B, all right, and you have a point P somewhere here. The shortest distance between the surfaces of the sphere is 6 centimeters. A movable point P lies along the line joining the centers of the two spheres at distance x from surface A. The variation in distance x of the electric field strength E at point P is shown. Okay. Use the figure to explain whether the two spheres have the same sign or opposite sign of charge. Whether the charge of A and B has same sign, opposite sign. Okay. Now this one, they did not give you the sign of the charge. You don't know whether it's positive or negative positive or positive positive, negative negative. But what they just told you is that the graph looks like this. Now this graph that you get is actually the resultant electric field strength from here to here, from sphere A to sphere B. Okay, whatever graph that you got here is actually the combined effects of A and B already. You see, this is the case of between two charges. All right, this question is a case of between two charges, and they're asking you to consider this region. This region here is the having the electric field that is the combine of A and B together. Okay, so whatever you get here is the resultant electric field strength of A and B combined together. Okay, so without going so much into that, then we go to the next question. They ask you to explain from the figure, how do I know the two spheres have same or opposite sign of charge? So as I mentioned to you, all you just need to do is you look at the end. What is the sign of the charges? You notice that in your case, your charges have your graph of E versus X now looks like this. So you look at the ends there, what are the signs? you see that this one and this one means this is opposite sign, opposite field direction. Therefore, charges have same sign. Okay, so your answer will be something similar to this. You will say that near to each sphere, the electric fields are in opposite directions. Okay, and then because of that, the spheres have same sign of charge. There's only 2 marks here. It's either the first sentence and third sentence. That one will give you your 2 marks. Or you could also write the third one. At the point between the spheres, the electric field strength is 0 because the fields are equal and opposite. Okay, but this one I don't think it really ties to this or this now. This is the blue color ones have a clearer meaning, right? Because the idea then was that to tell you if this was same sign, this is positive, or this is negative, this is negative. You put a positive test charge here, E will be here. You put a positive test charge here, E will be here. You put a positive test charge, E will be here. You put a positive test charge, E will be here. That's what this one means. Because they see that the electric field strength is in opposite direction, that one can only come about if you have same sign of charge. Alright? Okay. So that part is okay. Now, if you see that the resulting field strength is 0 at one point, that could also tell you that the signs are same now, because the idea was this: if this one is positive, this one is positive, I put a positive test charge here. If I say this is sphere A, this is sphere B, the field at point P is the field strength at point P is the field strength due to A and B combined together. So this is positive, positive, this one will be EA. Positive, positive, this one will be EB. So my EP at any point is actually EA plus with negative EB. It is because you have this negative here. At one point, E will be 0. At one point, EP must be 0. Okay. So if you can have E being 0 at one point, that would have meant that the field strengths are opposite direction in the first place. And if they are opposite directions in the first place, that can only come about if the charges have same sign. That one is to kind of explain this part. Alright. But to understand this, you need to look at this. Okay. This one is, I think, the one that is not really flowing that well. 1 and 3 will be flowing better. Okay. Right. Right. So that part is okay. Then if you are done with that, then you can have a look at part 2. Okay. Just have a look at part 2. Part 2, they tell you a proton is at the point P where x is 5 centimeter. Use data from figure 6.2 to determine the acceleration of the proton. Okay. Use the data there to determine acceleration of the photon. So have a look at the 5 centimeter mark. Find out what is the electric field strength there and find out what is your acceleration. At the 5 centimeter mark is somewhere around here. Find out what is the electric field strength here. Okay, you want to find acceleration of the proton. You know that Fe is equals to QE. As I mentioned to you just now, your Fe is your net force that causes the acceleration of your charge. So this one can be changed to MA QE. from which you can actually find out your acceleration. So if you're okay with that, then let me just plot this one. Okay. So at x equals to 5 centimeter, you should realize that your E is 3 times 10 power 3. Okay, the value of E is negative, but you don't really need to bother so much about that. We're only interested in the magnitude. So you don't really bother so much about the negative. Okay, so at x equals to 5 centimeter, E is 3 times 10 power 3. Then just now I told you that MA is equals to QE. This is just the derivation part. Your A is just going to be Q times E divided by M. The mass of a proton you can get from your data sheet, 1.67 times 10 power minus 27. The charge of a proton is 1.6 times 10 power minus 19. And your field strength is this value here. So you sub it in, you get your answer as 2.87 times 10 power 11. Okay, so that part should be okay, right? Part C you can't really do first because it talks to you about electric potential. This is the thing that I will talk about in the next part of your chapter. Okay. Just now I told you how to look at the resulting electric field strength if your charges were both positive. What if you have a case where both charges are having a different sign? One of it is positive, one of it is negative. How would then you analyze the same thing? So same thing as before just now, I mentioned earlier to you, when you put the two charges close to each other, the field strength of the electric field of A will combine with the electric field of B, giving you a new resultant field in this region. So by all properties you have here is actually the combined effects of A and B together. When you want to combine them together, you need to first work out what is the individual effects of sphere A and sphere B. So I mentioned to you that you will need to put a positive test charge if you want to test a particular point in the field. And then after that, you consider the individual effect of A and B. So in your case, if I put a positive test charge here and I want to talk about the forces, positive repel FA is in this direction. Positive repel, a positive negative would attract. FB is in this direction. Notice that the direction is a bit different from the previous page. Okay. If I want to expand it further again to talk about, say, electric field strength due to A would be towards the right. Electric field strength due to B will again also be towards the right. Okay. So in your case here, you see for A, it will always be towards the right. For B, it's also always towards the right. So force is a vector, E is a field strength is a vector, direction is important. If you have any opposite direction, normally we will give it a negative. But in your case here, you see none of them are in the opposite direction, so there's no negative, so to speak. If you want to talk about the electric force at a particular point, it'll just be FA plus FB. If you want to talk about the electric field strength at a particular point, it will be EA plus EB. So here there is no negative, different from the case before this, where you notice that they were in opposite directions, so you actually had to give it a negative. So in your case, you don't need to. So in your case here, you have this, just plus. And then you can expand it further to give you these equations here, just like the previous case. Now, when you want to draw your graph, then your graph will actually just look like this. Okay? If they are having unlike charges, the signs of the charges are different, you get a graph that looks specifically like this. Okay, so what you could say here, a few things here that you should note is this part here will never be 0. If you're asked to draw a graph or whatsoever for field strength versus distance or force versus distance, note that this part here will never be 0. Because you see, this graph is obtained from this equation as you vary the distances x, which in turn varies the RA and RB. Now this one here will never be 0 because you look at this. Your whatever values you get here is from some value plus with some value. Now, if you are adding only positive values all the time, you will never ever get a case where you will get a 0. All right. So when you draw the graph, please make sure that there is no 0. It will never ever be 0 because positive value plus with a positive value will never ever be equals to 0. It will be some value more than 0. Okay, so it will never be 0. Okay, then after that, your graph will look like this. Okay, you go closer towards A, the effects due to A is larger. You go closer towards B, the effects due to B is larger. Okay, and if you're given a graph like this also, you will also be able to identify whether the charges were in the first place same sign or opposite sign. Again, you look at this. What were the signs of the field strength or force at the ends? This one here, you see it is same sign, so therefore same direction. That will mean that your charges are opposite sign. Okay, you see that this and this have same sign, so that means to you the field strength is same direction, the resultant field strength is same direction, therefore the charges are opposite sign. The easy way to look at it is you visualize it like this. If this one was positive and this one was negative, you put a test charge here, obviously your E will be in this direction. If you put a positive test charge here, your E again will be in this direction. So therefore there are opposite sign. This is represented by this now. Okay, so in the other cases now I told you if you have same sign, like this one, if you put a positive test charge here, this one will be here. If you put a positive test charge here, this one will be here. This one is opposite sign, opposite direction. So your signs must be, signs of your charge must be same. Okay, but now here you see they have same sign, same direction. Therefore, the charges are of opposite sign. Okay, that's how you look at it. Okay, so this one don't bother so much. This is the one that you want to talk about, right? And then here, sometimes you could also talk about the speed also. If we ask you to explain a little about the variation of the speed of a test charge that moves from one end to another end from sphere A to sphere B, how will it look like? Well, we'll just tell you this one. Now, in your case, when you are moving from here to here, if I'm talking about, say, just the electric force, there will never be a case where my electric force is 0, as I mentioned to you here. Okay, when I move from here all the way to here, my FE will always be in some direction, in the same direction. Okay, but the magnitude, you will notice, will keep changing. At one point it will drop, and then at one point it will start to increase, but it will never ever change direction. So the conclusion you will be able to get here is that if you had a positive test charge and you're moving towards the right, your electric force is always in the same direction as your motion, or rather your acceleration is always in the same direction as your motion. You will always be speeding up. Just that when you're speeding up, it's a matter of whether you're speeding up at a decreasing rate or speeding up at an increasing rate. So for this part here, you actually be speeding up at decreasing rate because your magnitude of F and hence your magnitude of A is decreasing. But if you're talking about this portion here, you again will be speeding up but at increasing rate because your magnitude of F and hence your A is increasing. direction here never change. So you're never going to be slowing down. Now this point here is not the point of max speed. The point of max speed like just now is for this one. This part here we could say is max speed because here you were speeding up, then you stop speeding, then now you start to slow down. So your max speed is here. But for your current case here, this one is not max speed because here to here you're speeding up, here to here you're also still speeding up. This one is not considered to be max speed. All right, so just be careful about that. Right, so whatever I just explained here again is put inside this table here, so just take note of that.